Hi everyone, I'll be presenting our work on AI-driven crop disease detection and sustainable management, where we achieved state-of-the-art classification using advanced deep learning architecture. This is the table of contents and I'll drop right into the introduction. Rice cultivation is vital in Africa, but bacterial and fungal diseases threaten crop yields. Manual disease identification can be challenging due to vast farmlands and a shortage of specialists here. Automated detection systems can help improve productivity, but the lack of region-specific datasets is currently an issue we face, and we hope that upon availability of African-specific data, they will be fed into the same trained model that has high accuracy, reducing retraining time, and African farmers can jump right into detection. Our dataset is a balanced subset of the Paddy Doctor benchmark. This dataset contains 16,225 labeled RGB images, spanning 12 distinct paddy diseases and a class for healthy leaves. Our objectives were divided into three main phases. The first phase, which involved reviewing prior implementations to identify limitations and areas of improvement. We went further to re-implement the baselines to understand their architectures and confirm reported metrics in literatures. Lastly, we extended this work by introducing ResNet 50 and EfficientNet B0. Our methodology involved transfer learning, which involved fine-tuning all layers to adapt to paddy disease features in the image dataset. For the loss function, we used categorical cross-entropy with label smoothing to penalize overconfidence on rare classes. Batch normalization was also implemented for regularization after each convolutional layer, and dropouts were used in fully connected layers to prevent co-adaptation of features. We conducted so many experiments multiple times on different models, and of the 7, ResNet 50 performed best. Pre-trained weights from ImageNet were used, and the architecture has 4 residual blocks. Global average pooling was employed to reduce spatial dimension before the final layer. The final fully connected layer was a dense one with a softmax activation for classification, bringing it to a total of 25.56 million parameters with residual blocks and a bottleneck. ResNet 50's success in this work hinges on its residual framework, as seen in the chart, as it employs skip connections to mitigate vanishing gradients by preserving gradient flow through identity mappings layer by layer. The bottleneck design expands channels before spatial convolution, then reduces them back, providing a compute-efficient way to capture multi-scale features. For our result and discussion, we used 4 evaluation metrics. The accuracy measures the proportion of correct predictions from total predictions, providing an overall performance indicator of our model. Precision helped us to tell the model's ability to avoid false positive, while recall, which is also known as sensitivity, measures the proportion of true positive predictions out of the actual positives. And lastly, the F1 score provides a single metric that balances the trade-off between precision and recall. Our performance results are seen in the table. The ResNet 50 achieved 98.71% test accuracy, which is a 1.2% absolute improvement over prior work. Precision and recall exceeded 98.5% for all classes, including rare ones like bacterial panicle blight, which had 99% precision. Surprisingly, our ensemble of EfficientNet and ResNet 50 scored only 97.51%, and this can be attributed to feature space divergence. It is also likely to ResNet 50's deep residual layers learning highly discriminative embeddings, making ensemble average less effective. For our key insights, deeper residual architecture provided better discrimination between visually similar disease classes, and surprisingly, like you said, the ensemble model underperformed compared to single models, suggesting potential conflicts in feature learning. For ResNet 50's performance, we saw that effective residual connection allowed better gradient flow in this architecture, and the bottleneck design balancing computational efficiency and feature expressiveness. In conclusion, we achieved 98.71% accuracy on the balanced dataset, setting a new benchmark for paddy disease detection. This isn't just for academic purposes, as we envision it becomes a tool for farmers with limited access to experts. Future work includes deploying quantized model on edge devices and validating them with African field data. Thank you.